to cloud. Bam. All right. So last time we were looking at the amazing thing called limits, and ended class with looking at limits that does not exist. So let me give you one as a warm up for you guys to start with. It's the same thing every time. You show up to work and you start section. Limit as xy goes to 0, 0 of x minus y divided by x plus y. So it's that. That's it. So of course we know we're going to look at our 4 directional derivatives. Soon we'll look at directional derivatives. That'll be like in maybe a week or 2. We'll talk about directional derivatives. There's going to be directional partial derivatives that we can talk about. And then we're going to talk about that function called the gradient function that Jason has been so adamant about seeing since she's been asking about slopes for a while. But we know we're going to look at this in 4 different directions. We're going to say when x is equal to what? Y. When x is equal to y, I like it. And when x is equal to 0, and when y is equal to 0. And when y is equal to negative x, right? When we take it, we actually plug that bad boy in. What do we do when x is equal to y? Well, then we can just replace the y term with x. We'll have x minus x all over x plus x, which ends up being 0 on the top and 2x on the bottom, which evidently is equal to what? 0, right? We're happy with that. Then if we put x is equal to 0, well, that kills the x term, right? We'll put negative y over a positive y, which gives us what? Negative y. And we can instantly see that these two are not the same, and we are happy. But if we want to keep going further, well, we can plug in when y is 0, just in case. We'll see that we have x over x. X over x is basically y. And we can instantly see that none of these are the same. So therefore, the limit does not exist. Any questions about that? Too easy, right?
Yep. And you can plug in like, I think I asked this last class, but you can plug in any equation for y or whatever, like so y equals x squared, you can put that in.
Exactly.
And if the limit does exist, they should all equal 1 value. If it doesn't, they're all
Exactly.
okay.
But the only reason why you wouldn't do x squared or x cubed is they're going to complicate your life. But other than that, I think using these 4 right here are probably your best bet at this moment. And yes, Mr. Derek, you have a question.
Y equals minus x, that way get it undefined.
Yeah.
So that means it like goes to infinity or negative infinity.
In that aspect, yes. But in reality, it goes to infinity, we don't need to worry about that. We'll come back to infinities when we start talking about series and sequences and stuff. And yes, series and sequences are gonna come back. Alright, you guys loved this so much last year, right? So I might as well bring it back, right? Okay, I'm not sure if you guys hate it or you love it. Who likes series? A little bit. Alright. It's an acquired taste. Right at the beginning, you guys were gonna register for DPQs. When you're doing differential equations, there's one easy way to solve differential equations. By using series. Using series, you can solve almost every differential equation. It just takes a lot of work. And it's annoying. And you can take derivatives of series. Fun stuff. Okay, all right, so let's do another problem. And I'll put probably, who can I put on the board? Who wants to go on the board? Who likes the board? All right, so you're shaking your head, not mean you're going, "Oh, I'm sorry." Well, you shook your head no, so I have to make sure that.
You asked,
I'm sorry?
you asked me. You asked.
All right, so the limit as x comma y goes to 4 0. And we're gonna have 3 over xy. And don't worry, this one's not that bad. Ooh, sorry, that's just me being tired. Yeah, I didn't get to stay home and relax like Ryan and David. Okay, let's see what's the recording. I just been watching it right now.
Just want me to photo in and say
This around? Yeah. You got it. Like all 4 of them? All 4 of them. Let's get practice.
3 over 0, right?
Mm-hmm.
Okay.
Well, that's interesting.
Very. Leave that like that, right?
Cool.
That what you want me to do?
Oh, yeah.
Okay. Good?
I like it.
Alright.
All right, what can we say about these? Screaming in your head. Yes. Limit does not exist, of course. Limit does not exist. And also, if you think about this in the world of just even normal algebra, you had 3 over x. How does that graph look? Does anyone remember? Yeah, it's one of those annoying, right? Graphs that go like that and have a little going down like that. Well, at the center point, which is the origin, where's that guy? How's that guy look? Well, he has a vertical asymptote. So this is showing us, hey, even in this crazy world here, we are still going to have a vertical asymptote. The old ways of math does not change. It's always still the same thing. That's one thing I learned in my entire career in math. Everything comes back, repeats itself. Comes back in just a different guise. Never hear the different guise. It's very similar to this guy, but in 3D. Because now, what we're eventually going to do is we're going to see that's going to be equal to f of xy is equal to, or don't put equal to, well, yeah, you can put equal to 3 over xy. And right there, you know, oh, that's going to have the equivalent less, and so towards the origin. And of course, we know that thing's going to blow to infinity, and we're going to just cry for the limit. And just say, okay, there's really no limit. All right, any questions about that? Everything comes back with the bridge.
So for the first y equals x is x equals 0, or sorry, y equals 0, x equals 0, when it was the like undefined 3 over 0. Even though it's like 3 over 0 and 3 over 0, we still don't know, right? We can't say,
Exactly. Right. We can't say it's blowing up to a positive
it's just
infinity
kind of like,
or
well,
even a
we
negative.
can't make
Yeah,
determinations from that.
yeah. We have to do a further investigation.
Yeah, okay.
But the further investigation, we just break it down to the normal case that we remember from old algebra and say, oh, yes, it's definitely going to be further left. So, you know, one's going this way, one's going that way. So, right. Yeah. Yep. All right. Easy stuff, right? We want this on the next exam. Yes.
So with the limits of x, y, equals 0, does that mean that all kind of solve the problem? Are you supposed to plug in 0 or?
You can plug in 4 0, but you'll just get 3 z over what 4y, and if you plug in 0, we're still gonna get 0. So you get 3 over 0.
I'm just like wondering, like, what's the process, like, what costs you want us to show?
Oh, if you just show me this, I'm perfectly fine with it. As long as you can make a logical argument, I'm perfectly fine with that.
Gotcha. Yeah, we're less, correct me if I'm wrong, but to paraphrase what you just said, we're less concerned with the actual points of it and more concerned with just the limit exists.
Exactly.
Okay. So they're kind of arbitrary
Exactly.
for this problem.
Mhm.
Okay.
All right, so let's talk about a strategy. Just because we need to strategize. And the strategy that occurred for you is to show the limit does not exist. It is enough to show one, it does not exist. In a single direction. By single direction, I mean, if we're doing y is equal to x and y is equal to negative x, we can show that those two are not equal and we're done. 2 different limits along 2 different directions. That's when we're looking at y is equal to 0 and then y is equal to x. And here's a hint of caution. Oh, yeah. You cannot ever determine. Right to it. Cannot ever determine a limit just by looking at it. And I say this strongly because a lot of students in West Virginia thought that they can just determine a limit just by looking at it. And when they took the test, they were like, well, I just looked at the limit, and I guessed it was this, I was like, well, obviously it's not that. So you just can't guess, you have to do some type of inspection. So, no guessing here. Excellent. And what did they accept for your exam, was it 28? 28. Oh, sorry, wrong class. The 20th is 105. You're the 28th, so 10/28. I'll make sure I write that down again. 10/28, 2021. That's test number 7, right?
Also, Professor, I looked and finals are December 6th to 11, so December, whatever it was.
Second.
Yeah, second.
Would have been perfect.
No,
Why not? It would have been perfect. It was just 4 days for a final.
Give us a warm up.
Exactly, a warm final.
Sounds good to me.
I don't like warm ups. Don't you guys like to warm up? Like you go to the gym, you start posting up that bench press.
Max weight right away,
I'm sorry, max weight press.
200 pounds on the bar.
That's it? Okay. Wait, 200 pounds.
No.
Okay, I was scared for you. I'm sorry?
and it's December, did you like to hear earlier?
Oh, yeah, we're gonna talk about the new date for the exam, because someone said that they cannot make it. So how does the 30th sound? Of November? Yes, I believe, we have off, I believe, just listen to me. We have off, I believe, the 25th and 26th. And we come back, I believe, the 29th.
And then right away,
Alright, that works.
Yeah, that works, I think that's not bad.
You're dropping one, right? If you do that test.
Yeah, I definitely dropped.
Sounds good.
okay,
So remember, it's for your benefit. I want you guys to have the best score you can have. So even if you come and you fail that test, as long as you have other good tests, that won't get dropped.
So we have one more lecture right before finals. and-
Yeah, then we have one more lecture correct before finals, so we can laugh together, maybe have a pizza party. I doubt the pizza party. It's too late for pizza. I'm not sure about you guys, but I think if I eat right now, I start to like, I gain 17 pounds when I eat right now. So, be thankful with your rapid metabolism. Alright. So if we're taking limits, the next thing we're gonna start doing is what? Differentiating. We're gonna look for the differential, or in this case, we're going to take derivatives. But the derivatives are gonna be referred to as a new idea. This new idea is gonna be referred to as a partial derivative. Partial derivatives are fun. They're basically a derivative, but you're looking at it specifically at either the x or the y or the z or the w. You're going to be taking partial derivatives of independent variables. And then we're going to do partial derivatives of dependent variables. Because once you learn derivatives, the next thing you learned was touch of an I, not integrals, but implicit differentiation. Remember that?
yeah, I was close.
He was very close. Yeah, so then we're going to do the implicit differentiation, and then we're gonna go in deeper and deeper into our partial derivatives. And then we're going to learn the chain rule with respect to partial derivatives. So basically, we're going to learn everything again that we did in Cal 1, but we're going to learn it a little bit more slowly than we did with the vector value function. Vector value function, you're taking component wise. This time, we're going to be taking partial derivatives of several variable functions. So it's going to be involved a lot, because what can happen is you could have a we'll say a function. That specific function is going to require that you do a chain rule. Imagine doing the chain rule. Inside the chain rule, you have the product rule. And inside the product rule, you might have the quotient rule. You might have so much going on, you have to go step by step by step by step. Of course, you guys know how to do the product rule. Of course, you guys know how to do the quotient rule. Of course, you guys know how to do the chain rule. You know how to do all these rules. Which is why we're gonna probably breeze over this topic quick, but not too quick. Just because I gotta remind you of what to do. So, when we're looking at partial derivatives. We're looking at it in the world of 3D space. So we have X, we have Y, and we have Z. Now, I'll ask you guys a question. What is a partial derivative? Or should I say, what is a derivative?
Slope.
A slope. And you're used to looking at a slope to points, right? Now we're looking at slopes to 3D objects. This will be referred to as a saddle point. If you guys remember from Cal 2, saddle points.
Slightly, yeah.
Okay, good. So, if you look at it, we're taking a slope of a specific point. What type of problem do we see again?
Max and
Max and min, but a little bit more than that. Infinite directions. We're back to square one with the limit. We see that if we have a point in space, we can have a partial derivative going this way, we can have a partial derivative going this way, this way, this way, this way, this way, and we start to see, oh wait, we have an infinite amount of slopes. Do we like infinite amounts of slopes? Maybe I do. But do you guys? No. See, I like it because I study set theory. And when I study set theory, all I do is study infinity. But you guys don't like to do that. You guys like to get straight to the answer. I think I've been noticing that a lot with all my students. My students, even at the high school level, the first thing they say is, Professor, why are you showing us all this extra stuff? How do we get the answer? Like, well, it's easy for me to tell you the answer. That's not how you learn. You learn through experience. You learn by thinking. These kids don't like to think. You guys like to think, but you're still at that stage where you like to think, but you don't like to think too much. Like if I gave you an integral to solve and it took you about 30 pages to solve the integral, would you guys like to do that? No, I would like to do that. I wouldn't mind doing that because that's my life. But you guys are doing it. So now we have an infinite amount of solutions. So what are we going to do? Well, in this case, what we're going to do is we're going to say, okay, Z, that's going to be my dependent variables. So since this is my dependent variable, well, I'm going to take my derivatives or my partial derivatives with respect to them. So when we're doing the old partial derivative, like we're doing the old derivative, we have d dx, right? And also we had, so this is what Leibniz notation, Leibniz, whatever his name is. Yeah, and then we have the infamous Newton one, y prime. Me personally, I kind of favor both at the same time. Like I like both of them.
You could do d over dx prime.
D over dx prime. Yeah, so we're going to use these amazing things, but now instead of having it as a d, that's what we're going to do. We're going to make it fancy. It's going to be a curly thingy. This is going to be what we're going to reserve for the partial derivative. This is the notation for the partial derivative.
Is that a 2?
It's a curly D. So think of the D would add like an extra like maybe something like notes like that. Think of it like a musical note. Okay, kind of. So it's not like a 2, it's more like a curve. Alright, what's like a 2? I'm sorry. Sure. We're gonna reserve that notation for our partials. And then that's going to be the Leibniz or Leibniz notation. The Newton notation is very, very, very favored. Let's see. Yes, it's the best one. It's just an F with a miniature X next to it. Here's the thing. That's just X direction, right? There's also a Y direction. We're also going to have a partial with respect to Y. The cool thing is now we're doing real calculus. When calculus was first taught, it was taught in this way. And then years later, they found it was too much information, so they separated it. Which was a good thing, I think, for most people. Can't just throw a bunch of information. And then also in the old days, you hired a private tutor, right? Like when Newton was learning his stuff, he was one on one with a professor. We then found that Newton was the best, and he just made him like the chairman of the department, like Rothman. He gave up his position to give him there. Because Newton was just that good. I was telling my students this morning, I was like, Einstein, you're a genius, right? You're like, yeah. I was like, well, Einstein is nothing compared to Newton. Like, what do you mean? Well, I was like, well, Newton, he didn't agree with how the math was going, so guess what he did? I'm like, what did he do? Like, oh, he made his own discipline of math. So Einstein didn't do that. All Einstein did was Einstein's summation. Like, he shortened the summation. Whereas Newton just created an entire field itself. I'm like, wow, okay. So
Well, Einstein did a lot of physics stuff, it's not really a mathematician.
but he was good at math.
Very
He
good.
was good at math, really. But I believe the story is that his wife was better at that. Yeah, that's funny because Mileva Einstein was a very great physicist. Amazing, great experimental physicist. Not to mention she was one of the first female physicists accepted into a college in I believe it was Switzerland. It was like one of the top ones ever, and she was accepted into that as a female, right? When females were treated like dirt back then. So she had to be great if she was there. And the only reason why she didn't publish a lot of papers was because Einstein decided to run off with his cousin, and she had to be stuck raising the children that he gave her. So, yeah, right. Deadbeat dad. Well, that's what most dads do sometimes. It's not good, it's ridiculous. Alright, so let me redraw this picture, I'm gonna redraw it in a nice way. Because now what we're gonna end up noticing is, yes, we have points, yes, we have lines, but something else we have. What else do we have what we've been studying for this past few weeks? We have lines, we have points, we have line segments, and we had parameterized lines, or what was that? Planes. So now we have these planes in space. And I assure you, with these amazing world sheets, guess what you can find? You can find a line that does what to it? Touch it once. You can find a slope that says touch it once. So how do we account for it? What are we going to do? So we have to figure out a way to do that. One way to do it, as calculus was developing, is that this. Well, we have an x and we have a y. when we were doing normal, baby calculus, we were fixing a position and the dependent axis and taking that as a basis to find a derivative. We're gonna do the same thing here, but this time what we're going to do is, we're gonna say, if we're trying to find a partial with respect to x, we're going to make y constant. Meaning if we take y to be constant, what we're going to do is we're gonna see that we can find a point going through the x axis that's gonna give us our partial derivative. It's gonna give us that slope going in that direction. And give us that slice. Then we're gonna do the same thing with y. We're gonna see, oh wait, we can fix a y point and find a slope that's going through there as well. When we find a partial with respect to y, we're going to make what? Well, we're going to make x constant. We'll put a happy face there. Yes.
Is that a tangent point or is that, are those two lines just?
Oh, right now they're just a coincidence that they're crossing. But yes, we're gonna get up to tangent planes and we're gonna see all this amazing stuff soon. What I'm gonna do is, when I start doing the chain rule and go deeper into it, I'm gonna incorporate the chain rule for vector value functions. And we'll bring in integrals of vector value functions, bring in integrals from several variables. And we're gonna start doing applied problems. And I think from beginning of November to end of November, it's gonna be nothing but applied problems. All physics, all the time. Just because I love physics. Maybe I might throw in some marketing questions like optimization. That's boring, right? Yeah, we want to learn how to blow up the world, right? Oh, hey, you're smiling too much about that. Watch. All right, so let's open an example. We're gonna have f of x, y is equal to, let's take our infamous problem, x squared plus y squared. This we know is a sphere, right? Because z is our independent variable, we just change it as a function of x and y, and then we have this nice circle there. So, we're gonna take the partial with respect to x. What do we get? Well, we're gonna make y constant, which means whenever we see a y, it's treating like a constant. Which means the only thing that we're going to differentiate here is going to be x squared. What's the derivative of x squared? 2x. 2x. Simple and sweet, right?
So right, because the y is treated like a constant.
It's treated like a constant. So what you can do is, this is what I did when I took Cal 3 all those years ago. My Cal 3 professor, he didn't speak Mandarin, he didn't speak Cantonese, he spoke Fukienese, because he was like from the southwestern part of China. He speaks Fukienese. So he had this thick accent. I was like, I don't understand a word coming out of your mouth. But to teach myself, so I said to myself, well, if I want to treat it like a constant, well, can't I just picture it like this? Like some constant. There's some constant, you take a derivative of the constant, that just drops out. I picture that in my head and it helps me out. So you could try that also. Now, if I take the partial with respect to y, well, x is my constant, right? Which means x drops out of the picture. And what's the derivative of y squared? 2y. 2y. The cool thing is just 2y. You don't have to do a dy dx. You remember that when you're doing implicit differentiation, you were taking the derivative and attaching this guy at the same time.
2y y prime.
Oh, you're the white prime? I'm sorry. But, that's another way of doing your implicit differentiation by having the leave as notation. Line as, however you want to say the name. But now, get comfortable with taking those several variables, because what we're eventually gonna do is, we're gonna say, okay, we're gonna have 3 variables. And we might even have 4 variables or 5 variables. And with these multiple variables, we're gonna have to take multiple partial derivatives with respect to making specific variables constants. And we're gonna have to investigate how to do that. That's really easy, something you guys know. So here's a problem for you to try right now, which is pretty easy. Just because going back in history, we're gonna say g of xy is equal to e of 2xy. So find me the partial of x and find me the partial of y. And we'll probably put the other Joey on the board. Keep in mind, don't forget your derivatives, don't forget your product rule, don't forget your quotient rule. We'll, I'll do maybe one example to review that, and then we'll do partial derivatives. That's all I'm doing is one example, just because we have a lot to get done. And by a lot, I mean we need to, what's that phrase? Just brush over this stuff, because that's not the interesting stuff. You guys know how to take integrals, you guys know how to take derivatives. You guys know how to do all these rules, because that's what you did when you did your Cal 1 and Cal 2. All we're doing is just adding an extra variable. I think this entire class will only just looking for partial derivatives and implicit differentiation. Tuesday we'll do chain rule problems, and then we'll touch upon some optimization problems, word problems, and then some integrals, and then it's just going to be nothing but applied problems. Thank you, sir. Do we all agree? Yeah, right, because we're taking e to the x. E to the x is just basically e to the x again. Then we have to do a small little what here?
Substitution.
Substitution, a small little substitution. When we do that substitution, we see we get 2xy, then we differentiate that 2xy, well, we know that this guy's a constant, it comes along for the ride, it becomes 2y, e to the 2xy. Same thing for here. Now we're going to do the same thing, but this time, y is the one that we're looking at, x is a constant, comes along for the ride. Any questions at all? Easy stuff, right? This should be, I should make one test just all on this, right? And you guys will love that. Except when I bring the chain rule in there. Okay, so let's get a little, let's just throw some definitions down. So what does the derivative of a multi-function look like? What do you think a derivative of a multi-function example look like? I lost my words right there.
Yes, say multi-function, you mean like a composite function, or like just several variables.
Several variables, multi-function, composite functions. Yeah, all that stuff.
Is it a combination of all partial derivatives of each individual variable?
What do you mean by a combination?
I'm not sure, I'm just
Like a sign.
I'm just thinking through it.
Yeah, no, because you're thinking, because what is a road? It's a slope, right?
Right.
So we could have a straight line, and we can also have a flying in the space, plane, you can have an actual plane that can touch our function once. So that's what it's gonna look like. It's gonna look, what we're gonna do is we're gonna look at just the line case first, and we're gonna say, oh, we can make a plane of values. When we make this plane, hey, it touches that function once, and that plane can describe so much. But now it's touching every point of that specific thing. It's amazing, it's beautiful. You can think of it like what's the best word? So you can have this nice cylinder right here. You can have a nice plane. Just touch it once. Touch it once. And we're happy with it. And then we could think about doing special stuff to our planes. It gets really remarkable. Now when we were looking at 3D shapes. Now we have these 3D shapes, we have these things that are touching it, and so much is happening with that. One of the problems I wanted to give you for your project, I was like, oh, I can get this project, this problem yet because you don't have all the level of math that I want you to have for that one problem. It's basically a docking problem. You're looking at the International Space Station. Looking at the International Space Station, what do you want to give your astronauts? What's one thing that we all need? To live. No, what we need is to stay alive. Water and food, right? So what we want to do is we want to make sure we get this stuff. Wow. So are you sure you want to be an engineer? You're going to be the head of the engineers, make all the money. So yes, what we're going to have to do in this problem is we're going to have to try to asymptotically touch the doors. If we come in too hot, what happens? The crash, right? Blow up. Space station gone, everything's dead, right? We don't want that. What we want to do is we want to make sure we touch it. We come in too far away, what happens?
Miss it.
You miss it, and then all those nutrients that you were trying to get to the space station, what happens to it? It's gone, right? It went bye-bye. We don't want that to happen. We don't want to waste resources. And we have to shoot another launch. You think NASA likes to do that? No, because you guys should hate it when NASA does that. Why should you hate it if NASA does it? They shoot and those resources don't get to the astronauts. And you have to do it again. And then it's gonna come out of our pockets.
Right.
Do we want that to happen? No, I don't want to be, I barely get paid, so it's gonna come and take more money from me. I don't want that to happen. So what we need to do is we need to make sure that we come in a way where we can attach like a little door, and then suddenly, ooh, we're good. Because one thing that we're gonna do is once we're shooting, when we're shot into space, what happens when something's in space? Keeps going at that specific velocity. We don't have enough fuel to come back, so we're not gonna keep shooting fuel on our rocket because it's just, that's not we'll say cost effective. Especially when it's coming out of my money. I'm poor. I got money, we right? You don't want to waste useless money. All right. What do we also know? Well, we know f of x, y is a surface. In R3. The surface. It's a sphere. It's a nice plane. It's a nice 3D dot, right? It's a surface. We're looking at surfaces. Now we're trying to figure out how to take a tangent line through that circle. That does a lot, that tells us a lot. So figuring this out by using those partial derivatives. So here's another question for you. Is it the slope of the surface at a point? In a way. It is, and in a way it's not. This is a little, let me say, a little too ambiguous. A little too ambiguous. Yes, sir.
Depends on the direction.
We're gonna have to then take into account direction that we want to look at. And when it comes to looking at directions, what are we doing to get? We're looking at W V. Vector. We're gonna start looking at vector value functions again. And we're gonna start taking directional partial derivatives. And then we're gonna look at double integrals and triple integrals and all this fun stuff I'm so used to looking at. So this is what we are doing when we look at these partial derivatives. We need to know the direction. We don't know we don't know which direction we're gonna look at, then there's no point in even looking at that or any questions about that? Easy concept, a little hard to put into words, but I think it's pretty. All right. So I'll reiterate it again to find the slope of the tangent line. And the x direction. We must contain the tangent line in a plane parallel to the something
X-ray.
very, very close. It's the axis. And we want to look for the slope of the tangent line in the y direction. We must contain the tangent line in a plane parallel to the YZ axis. Any questions? Not too bad, not too shabby. Good stuff, right? I think it's good stuff. So we can write it in this form. We write in this form, we just remember that we're going to hold a y constant. For mathematicians, we want to be, separate. We want the notation to be perfect, just because we want to know how to differentiate it between what we did in Cal 1 versus what we do in Cal 3. I'm just going to hold dx constant. And of course, we know we can write it as f of sub x and f of sub y. Now, this is going to, now think about this, right? When you learned about derivatives, even before you learned about implicit differentiation, what's the next thing that they taught you? If you take one derivative, you can do what? You take a second derivative. You can take a single derivative and then take another derivative. So this is what's going to happen. So this is simply, yes, you can copy that down. But think of it like this. So actually, let's just make our function. Let's call it f of xy. Yep. Flow chart. Now, what are we going to do when we're selecting our directional derivative? When we're selecting our partial derivative, what's the first thing we're going to say? We're going to take the partial with respect to x, or the partial with respect to y. That means we could take the first partial with respect to x, or we take the second partial, the first partial with respect to y, right? Now, what I can do? I can take the second partial with respect to x again, right? I can say second partial with respect to x. Same way I take the second partial with respect to y again, right? But do I need to do that? No, because what can I do? I can take the second partial with respect to y if I wanted to. This is where it becomes a little shaky. When it comes to Leibniz notation or Leibniz notation, we want to make sure that we do that. We want to put the x first, second, and then the y first. We're taking that second partial. Anyway, if we do it here, we're going to do this. We're going to take the partial. Secondly, we're going to have dy and then dx.
Those two are equal,
All the time. We want them to be equal, not all the time, just because we're going to see that we're going to have functions, and when we take that second partial, it could be something completely different. And if you want to blame anybody, blame Trey. It's going to be unique. Love that word, unique. And look what happens. Then we have even more possible. It keeps going. Basically, like that amazing chart that you see in statistics, And just keep on going. Until we get back to constants. Because once we get to a constant, then it goes to goose egg, right? Any questions about that? And now when it comes to Newton's version, you do f of x and f of y, and this will just be f of xy. Oh wait, no, sorry. F of xx. And this will be f of xy. When it comes to Newton's notation, it's reversed. This will be f of yx. This will be f of y. And so on. So I think maybe when it comes to partials, Newton's notation might be a bit easier, just because you're not writing all this extra DD stuff. So I think Jason will probably favor this, but she spoke about line drawing. Any questions? Not too bad, not too shabby. Great. Let's just jump into more problems. Alright, let's see an example. We're gonna have f of xy is equal to 2x squared y cubed minus 3x squared y plus yeah, you can do 3x squared plus 3y squared plus 1. So we're going to use Leibniz notation for this one. Find me the partial of x and the partial of y. And on this portion, we'll put maybe Derek in the board. You got to call it a heartbeat, so do this one. So. Get a little funky. Just do this. I'll make some volunteer. It's amazing. Well, we the first two, and then we'll probably put Jason on board for the other two.
Alright,
I'm sorry.
we'll do the first.
Well, he started it already, I'm sorry.
I don't know.
Or do the first, do the top two, and she'll do the bottom two. Are you okay, Jason? Is it okay? Yeah, just keep going. She gave up on us.
We're solving it right now, you know, we're solving it.
Oh, yeah. Got this. We'll do the last two for her. Thanks, sir. Yep. Wait, this is being recorded. Mess up.
Should, we get like a test to 14.10. All of 14.
Oh, do you mean
Like by then.
by the end? No, we won't. No. I'll make 14. I'll make sure that I'll have 14.10. Maybe I'll test 3. You okay, Jason? Taking a second part here with respect to words. Okay, I like it. Which one do we hold to be constant?
We should keep the X there.
Why not? Now, does the second term have a y? And what do we say when we have no term?
Zero.
Just a constant, right? And the derivative of a constant is 0, so that means that 3x squared is going to do what? Perfect. Excellent. That is the last one.
What were you saying how to do this then?
So we took the partial with respect to x first, so that means we're looking at this guy now. Now we're going to take the partial of y.
So we're gonna take the partial away for this one.
Yes.
Hold X constant if you're gonna.
Don't be afraid. So we all agree. What if I told you? Oh no. All right, so far so good. That's good. I'll give Chase a second to copy it. Oh, good. I couldn't remember if I put it to recording. I You guys didn't watch the recording?
If I need to reference something.
Oh, crap. Let's get funky. Let's do this one. Say f of x, y is equal to e to the x cosine of y plus e to the y sine of x. Let's tackle that one. What are we supposed to do? Oh, sorry. I'm always gonna need to change the Newton's and Leibniz notation, just so you gotta get used to both of them at the same time. Anyway, is it worth it? Can you catch? Do we all agree? Why did we take the product rule?
This e to the x is a constant, it's just like a number. Or sorry, the cosine of y.
Cosine of y. So we can see that right here. So this guy right here, just a constant in that world, right? And if we look at this guy right here, wait a second, also just a constant. No P R. Not Puerto Rico, but truck. And when we took the partial with respect to y, well, at that point, e to the x was a constant, right? And then sine of x was a constant. So again, no product rule needed. Instinctively, you might say, oh wait, that looks like a product rule. It is a product rule, but in the world of partial derivatives, not a product. Good stuff, right? Alright, let's increase the difficulty. E is equal to x e to the xy squared. I want you to find me the partial with respect to x and then the partial with respect to y. We should start the teacher segment program. Each teacher has to get a, segment.
Public, health and safety. That's Zoom into the call.
You're right.
It'd be fun though. I'll become a teacher.
Just for the segue, right?
Exactly.
Now, when do we know this is happening? We have to use our favorite thing, right? One. What favorite thing is that? Product rule. So, what is a product rule? Do you remember?
Through the first times the regular second plus the first times the regular second.
Yeah, and the cool thing is when it comes to product rule, it doesn't matter if you look, you can always interchange it because when you're adding those two, you can do what? Meet it, so it doesn't matter how it's done. When it's gonna, you have to be very specific about is quotient. That's when you have to say, oh wait, there's a song to it. Comes with the song, then another song, the quotient rule. Okay, good, because I'm not gonna sing it, nor am I gonna dance. But the product rule we know is gonna be times G prime plus F prime times G. And the quotient rule, here's the cool thing about the quotient. So I get to the point where I just hate the quotient rule. So what I did to the quotient rule is this. So let's say I had a function, let's say x squared over like some other function. Let's just say 2x. Well, isn't it safe to say that we can change this into this guy? Like we can bring that function up. We can say e to the -1. And you have -1 and then you have the x right there. Then you can use the product rule for that guy. You don't have to ever worry about the quotient rule. But of course, I'm going to force you to do the quotient rule.
I didn't know there was a way to memorize the quotient rule by interpreting dance.
So there's a dance for the quadratic equation.
Never heard of it.
There's a song for the quadratic equation. It's what we teach to high school students because they hate being there in the first place. Let's just say hate being there. Guess what we don't like to do? Torture them. So we make a song. Then we make a song, and the song works really well. So usually people say high D low minus low D high over low squared. But they make it into a song form. I'm not saying that song for you, but that's the quotient. All right, so here we're gonna have to use the product. So we're gonna do the partial with respect to x. What are we going to do? Well, we're going to say, well, we know this right here is multiplied by this function right here. So let's put someone on the board. Mr. Mason, do you want to find me the partial of x? You got this. I think. Oh, shit. Or that was a call. Sorry, I'll take that plus feedback. So,
91.
you want to do what? Really? You're volunteering yourself or what? Let's
What,
go.
is it a trick one or something? I thought I.
No,
was
not a trick. I just didn't think you were gonna volunteer yourself. I was gonna go back to Joey. You can just say Joey's late. Other Joey. Thanks, sir. All right, please.
Wait,
You okay?
I got the first one wrong.
Did you?
I did.
Well, this is right.
Doesn't the y squared come down in the second half of that problem?
Yeah, that's what I heard.
Why?
Because it's part of the function's constant there.
So what you're saying is a constant, we should bring down the y squared
In the second half there.
in a second.
Can I move it?
Do your zy, and we'll focus on z.
I think everything else right.
That's it?
It was 0.
Was there a way?
Can't see it.
You get-
No,
Alright, okay, if this is wrong, you just.
no,
stop
I'm not
that.
saying it's wrong, I'm just saying. Tell me what's going on.
Well, I got, well, I did like UV prime, like, you know, the equations, I made like 2 sets of it for U prime and V prime.
Okay, show me everything.
Alright,
And what is your U then?
0 times. Plus, that's.
Okay, so what I'm saying is, okay, all right.
I did it wrong, sorry.
I got it.
So what you're saying is U is X then,
Yeah,
and then V is what?
say X plus 3.
E to the X, Y squared. Well, like, another reason why I'm gonna hate UV is because when you're doing, like, well, then when you're doing integration, you have to worry about that, right? Yeah, remember, integration requirements that you had UV? Yeah. So, this is perfect, I love it. Okay, so yes, Mr. Mason, when you're gonna do this, you're gonna get E to the X,
Yeah, I forgot. Square it.
and yeah, you have to do that bad boy, and then what happens? Oh, your Y squared comes down. Any questions about it? None, right? Then you could probably clean this up, you could probably factor out the E, the X, Y, and then do all that funky stuff, but don't worry about factoring it out. You can leave it like that and perfecthappy with it. All right, let's do another one. Let's see. So. Could probably throw a screwball. Throw a screwball at you guys. Here's a screwball. Some people can't hit screwballs because they're annoying. D is equal to Y to the X. And I want you to find the partial respect to X. No, I want you to find the partial respect to Y. Yes, it is. Actually, let's stop using this notation. Let's go back to the Leibniz. So. Smartphone, but could it also act like someone's TV at home?
I assume.
So just a test to see if you guys remember all of your diverse.
Is there an element involved or is that the entry?
Hmm?
Is there an element involved in the entry or is that the entry?
There might be an element here. All right, what you get for the first one? And
And Y to the X times Y.
how'd you get that? I'm not saying it's wrong, how'd you get that?
What?
I'm not saying it's wrong, how'd you get that?
I just, did logarithmic differentiation.
So what you're doing is you're relating it to 7x, right? Like 7 to the x, what's the derivative of 7 to the x? You're just gonna, the 7x comes down times what? Times what? You just said
Well,
L on the 7, right? Amazing, right? When we're doing the element, when we're differentiating e to the x, what are we actually doing there? We're doing e to the x times what? Ln of e, and what's the ln of e? Just one, that's how we get e to the x back. Same concept. What we're gonna do is, oh, we take the derivative of this to get the y to the x down, and we get the ln of y. What about in the y case? What are we going to get?
Y to the x minus 1 whole times x.
So we're gonna have x, y to the x minus 1. You see that, right? Amazing, right? So this is one of those like curveballs that you'll see on the test. Just because it tests your knowledge of normal derivatives and stuff like that, but it's always have variables instead. For those variables, we still work with. Alright, good. It's gotta be good. Let's see, I think I had one that had a caution. Oh, yeah. That's the next one, actually. Go back to black, so we're gonna have g x of y, that's gonna be equal to x squared, cosh, of x divided by y. Hopefully you guys know what cosh is. If you don't, let me know, I'll let you know what it is.
What are we?
Oh, sorry. We'll just make it simple again. dg of dx, dg of dy. Guys, what is cosh? Hyperbolic cosine. Hyperbolic functions come from the unit hyperbola. You have a unit circle, you also have a unit hyperbola. The only thing you'll have is a unit ellipse. Makes no sense to have a unit ellipse. Because a unit ellipse is just a unit.
Could you please give us the formula for hyperbolic?
Just use the derivative of caution, which is equal to hyperbolic sine.
I don't even know what. No,
The derivative of caution is hyperbolic
I
sine.
don't think, because there is like, it's like x or e to the x or, minus e to the x, there's something like long thing, but
Yeah,
you know,
that's Euler's, like using Euler's formula.
if you want to like actually get the numeric value.
Yeah. I'll probably make you guys like a 10-minute video on the unit hyperbola. And you can show you how we use it with Euler's functions and stuff like that, and get you guys ready for Euler. You're gonna be using Euler all the time, because all of you are taking differential equations, right? I mean, taking it next semester. Well, I'm not sure about the teacher, but you're taking it, right? Oh, am I taking it?
Are you teaching it?
No, I'm teaching it. No. They haven't told me what I'm teaching next semester.
Tell me you want to teach it. Tell them you want to teach it.
I'll tell them again, but then they might not give it. Oh, well.
What if we start student uprising? We'll tell them nobody takes
Eric might want to teach it, that's why.
it.
He was supposed
Start
to-
uprising.
He was originally supposed to teach it this semester, but forget to what happened, since the enrollment dropped. He wasn't, able to keep the class because since he's a full-time faculty, he needs, like, we'll say a full-time schedule.
Somebody's stuff is under the stove.
Okay.
I'm thinking it's supposed to be easier.
Relatively easy, I hope.
Struggle.
The way I did it.
I'm
yeah.
struggling.
Remember, this is your first time seeing partial derivatives. If you're getting it, that's
Yeah,
good.
I didn't
Not getting it, that's still okay. What I made sure I did was I made sure I had at least 7 to 8 examples
Yeah.
of partial derivatives, so you can go through them.
Now I'm not gonna watch this video.
I'm sorry. That's okay, we're gonna put Joey on the board.
I don't know.
That's
I'll walk
okay,
you
that's
through
the
it.
best.
Well, you walk me through, I don't even know where to start.
Start by walking up to the board.
Like, I wrote nothing down.
I'm sorry.
Alright, so what are you gonna do? So, for X, I just took the whole X constant.
Looking for X, we wanna make sure we hold what constant?
Y constant.
Why, yeah.
So the factor. Okay, and then is this the product rule? Or no?
Why?
Right?
Alright, do we think it's a product? Who thinks it's a product?
I think it's product.
Okay, cool, so, the product, so the first thing you should do is do what? Over here on, just subscribe for it. First thing you should do is write down the product rule formula.
It's the first time.
Just write it down, trust me. You want me to walk you through it, I'll walk you through it like I walked through it in my head. You write down that formula, perfect. Perfect, so what do you need in this formula? We need F times G. So write down what F is and write down what G. Perfect, now the next thing you're gonna do is you're gonna take the partial of F. What's the partial of F? You're doing the partial with respect to X, which means you're gonna hold Y constant, right? Is there a Y as a function? No, so it's gonna become 2x, right? So then write down here, just put F prime is equal to 2x. Perfect, and now you're gonna do G prime, what's G prime?
Inverse, or not inverse, sine, hyperbolic sine. X over Y.
Over what?
Y.
X over Y, perfect, but what's inside that function? Oh, so look at it, it has something inside, so we have to use A, so C. Maybe maybe a mini chain rule?
Oh, is that right?
Yeah.
Well, that's where that's okay.
That's fun. You're here not to mess. Actually, you're here to mess up. You're here to mess up and you take the test. Exactly, like the military.
So wait, but I'm holding Y constant still.
Yeah, but if you look at this is this X over Y. So we still got to differentiate this, think of this as X over a number.
I'm lost.
Okay, don't worry, let me grab this from here. So remember when we were doing like sine. Like X over 2,
Yeah.
what's the derivative of that guy?
I don't know, I'm lost. I thought it was. Wait, do I take the X out?
What do you mean by check the X?
Oh no, I'm totally lost here.
Say the derivative of the stuff inside the fence.
Yeah, I think the derivative of what's inside of parentheses, it's a chain rule.
Yeah, that's the derivative of the outside, that's the derivative of the inside. right?
Yeah,
So what am I messing up?
so you take the derivative of the inside, what do you get?
Oh, that,
Yeah,
1/2.
1/2, and when you get your derivative, you're gonna have cosine of what?
Oh, wait,
X over 2, right?
I
At the end, and then times what?
I pulled 1/2 out. This screwed me up.
But it's not a 1/2, it's when you're pulling out a
Why?
One
Over Y. Yeah,
is the constant.
Oh,
It's just like-
there's where I messed up. So it's 1/Y sine hyperbolic of that.
Yeah.
perfect, and now you get everything you need, now just put it together in that formula.
Alright, yeah, I butchered that, okay,
You didn't butcher that, you did good.
very good. They just do me a simplifier, or have to write times that.
Sorry. Shoot. Oh, Lord, these masks are deadly, it won't poke me in the eye.
Oh, no, those metal things.
Yeah, the little metal thing on the front. Alright, perfect,
No. Quick times that,
and what's that?
quick times G. G times F front, okay.
Perfect,
Thank you.
you're welcome, do we all agree? Yeah, alright, who wants to do the partial with respect to what? Easy. Just remember, any test is not gonna get C. Word.
If I said it used to an action. You're wrong.
No, sorry, I thought I got it.
It's just in the pressure of it. What's wrong? That makes me nervous.
And if I told you that that's not Omega, I'm kidding, it's like. Alright, but Jace, wanna show all the steps for Joey?
Why'd you point him out like that?
I'm sorry.
No, it's okay.
I wanna make sure he's 100%. And also, maybe David or Ryan at home is not understanding either. Very, very bad story. I'll teach you. I went blind because my master had.
It's like the ultimate dog eating homework.
Yeah.
I can't wear my mask yet. I don't know.
The sad thing is my left eye is my good eye. Looking terrible.
Oh,
What are you doing?
you know what? Sorry. I was just moving a number.
We see what happened, right? We saw that, okay, this is just x squared times something. What if this x squared is times something? Well, technically, in a way, if we're holding x squared to be constant, do you really need a product? Constant multiple. So we can still apply the product rule works for every function. Every function has a product. But sometimes it's so redundant, you don't have to use product. But technically, if you think about it, this guy is just x squared. We don't have to even think about taking a product rule because it's just, think of it like think of it like 3 times the cosine of, we'll just say, we'll take this guy again, x over 2. When you evaluate this, do you use the product rule for here? No, you could though, but you don't have to. You can just say, oh, this is just the sine of whatever, right? And that just comes along the right. So the product rule here, I'll just make a note of it.
Is this supposed to be?
Oh, it is supposed to be, yes.
Oh,
Product rule not needed. You think about it, if that 3 comes along for the right, right? 3 comes along for the right, so that's this constant is coming along for the right, so x squared is coming along for the right. When you take the derivative of this guy, x comes out, x times x squared gives you x cubed. And of course, since we know that this y is in the denominator, the power is gonna get higher. So I know it feels a little salty right now, but after you do a bunch of problems, you do them over and over and over again, you'll understand. If you need to watch the video again, watch the video again. It'll work out all the time. Think of it working out all the time. Let's do, I think we have time for one more. This time, we're gonna have W is equal to 2x cubed plus 3xy plus 2yz minus z squared. Now I want you to find me the partial of x, the partial of y, and the partial of z. You probably say to yourself, wait, how can we do that, Professor? But what is a dependent variable in this case? W. W. I'll teach differential. Really hope that class. How many years is it now? 2021? I told that in like 4 years. Sorry?
Come on, yeah.
I know, I need to add that to my resume again, it's been too long. Actually, the class that I want them to do, I want them to give me a set theory class. I would love to take a class on set theory.
But you even have like you said, maybe.
So they have like a truth-based course, which is like called Intro to like Advanced Mathematics, which teaches you nothing but proofs. So after you take Cal 3, linear algebra, and differential equation, you take a class called the Bridge to Advanced Mathematics. And that class teaches you how to write elegant proofs. And the entire class is just proof theory. And I would love to teach a course like that. But I think they have it here, but they only offer it during the full semester.
They have it here.
They have a variation of it, so the differential equation you're gonna take is gonna have some linear algebra in it.
There's like I saw that there was something here algebra class just
Alone, but I think it's rarely offered.
I like seen it once.
And you're gonna offer it soon? I would love to teach that course.
I think we're trying to get it.
That'd be the best course to teach, because
There
there
were
were things,
things like 0 students ordered, like nobody, I don't think anybody got into it.
that sucks. Like I said, I would love to teach that course. Why? Because it's easy. And
Oh, actually,
Mason would love it.
when I was taking summer, the teacher said that they just published it here at LTRC, so it's like new. It's like
Oh,
like a year old, but it came out like a year ago or something.
All right, that's cool. All right, Derek, since you're talking so much, switch on the board. With the blower. I'm excited. I want to beg them to give me that class. I would love to teach you guys differential equations, but they give me linear algebra. So,
You take difference for that or not?
you can take them both at the same time. It's recommended to take it both at the same time because once you start doing a series of differential equations, you have to use linear algebra. So. All right, so let's go through this. So if we're gonna take the partial of, with respect to x, well, we get 3 times 2 is gonna give us 6x squared. And we're gonna take the partial of here, so look what happened. The 1 comes down, x goes away. Does this have an x? No, it goes away. Does this have an x? No, it goes away. Then we do with respect to y. Does he have a y? Nope, constant. And we get 3y. Or no, we get 3x. And then when we take the partial here, what do we get? We get 2z. Does he have a y? Nope, goes away. Now we look at the z's. Well, does he have a z? Nope, goes away. Goes away. Then we look at this, 2y comes down. Then we do z squared. Well, that just comes 2z. And we're done. Any questions about that? Really, really easy, right? Easy stuff. Alright, so any questions about basic partial derivatives? None. Okay, all right. So now we're gonna get a little funky. Implicit differentiation. So in the world of Cal 1, when we're doing implicit differentiation, basically what we did was we noticed that our dependent variable was y. Now, in this world, a dependent variable is going to be z or w or some other variable. We just need to identify the dependent variable, and then we can do everything that we did before. We get our y prime, or in this case, we're going to get a z prime. We're going to solve for z prime, and we're just going to play with it. So we'll do one example together, and then of course I'll have an example. All right, so we got 10 minutes left. Could they do this in 10 minutes? Too deep. All right, so what do we know? I'll just say this. Z is the implicitly defined variable, not y. And then we're going to always differentiate everything. Everything is differentiated. So here's the example. I'm going to try to not fly through it. It's going to be x squared y plus x. I don't like that x even. Xz plus yz squared is equal to the ocho. So what are we going to do here? Well, what I like to do, you don't have to follow it. What I like to do is I like to say, okay, what I'm going to do is I'm going to take the partial with respect to x. And if we do the partial with respect to x, we also got to do the partial with respect to y. So we're going to implicitly find our partial with respect to x first, and then we have to find our implicit with respect to y.
What about z?
Z is the
Oh, right, it's the,
dependent variable. So we only have to do z if we had a fourth variable.
yeah, right.
So this right here is bad notation. What I mean is, no, so I don't think Pearson's going to require you to type it in. But if you take differential equations and I'm not your professor, this is bad notation. Don't do this. This is just a helper. Basically, what we're doing is what I do in my head is I distribute this to every term. Just so I don't forget. And since I'm very kind, Professor, I'm gonna do the first one. Partial with respect to 8, that's gonna be 0. I'm so kind, right? And now we do the partial with respect to x and y. Here's the thing. Think about it. If we're taking a partial with respect to x, let's look at this guy right here. What do we notice might happen here?
We're gonna isolate the z variable.
Isolate the z variable. But something might happen too, right? There might be a, so it's a p. Might be a product rule. So he might have a product rule. Because if you think about this, isn't this like basically multiplying the two functions together? And we're taking a partial with respect to that. We have to also take a partial for z because we need to get that implicit thing. So basically, when we were doing tau 1, we had an x and like a y. And we have x and a y, we had to apply the product rule there. So we're going to have to apply that product rule here. Blessing is this other z, do we have to have a product rule there? No, because y is just a constant. So at the beginning, you guys are going to mess up your partials just because, hey, it's something that you're not used to. Know that the calculus is just annoying when it comes to those partials. Okay, and we got 6 minutes left, so we're hoping I'm gonna finish this problem. So I won't spoil it. And I'll say, how about this? Try yourself at the end of today, or Friday, or Saturday, or Sunday, or Monday. Come back to this problem, try it yourself to find dz dx. And that goes for you too, David and Ryan. Try it yourselves. See if you can get an answer, and then when it comes in on Tuesday, I'll finish it all for you, and we'll compare answers. See if you're understanding it. Because doing problems is going to make it easier for you. All right, any questions?
How many, what, number in the homework did you get up to this class?
I think you still might be on 14.1, 14.2.
Okay,
Yeah, I think 14.2 or 14.3 might
pretty
be
much through 14.2. This is it, so it's probably at 14.
might be 14.2. Okay. Oh, you really went to 14.2?
Most of it, I have like two problems left.
Okay, cool. Wow. On top of everything.
Mm-hmm.
Do you like 14? Chapter 14 so far, or is it hard?
It's not terrible.
Not terrible, but it's not easy.
No.
Okay, all right. Well, my examples hard or easy compared to the Pearson stuff.
There's definitely a lot more than Pearson.
A lot more than Pearson. Yeah. The only difference is if I did those like hard problems, they'll probably take all class just to do one problem.
Right.
So, but sorry, but
I
yeah,
mean, most of like the basic stuff, right? You know, you just apply the same principles to the more complex stuff.
exactly. Yeah. All right. So I also posted your first project. It's basically from the textbook, and it's I think it's page like 3 something. Yes, and I put it on the announcement. It's questions 1 through 10. You just go through this questions 1 through 10, and basically everything is from chapter 12. It was like a nice review of chapter 12, and then your next project, I'm thinking I'll put it it's like a 100 questions for 14, and then your last project, which I want to give you in like late November, that's going to be an actual question, like that docking question I was talking about. And you have to think about it, and you have to go step by step by step, and you'll use everything that we learned up to that point, and then you'll say to yourself, wow, this was a really nice optimization problem. Any questions?
What is the project? Do? That's probably in the, but,
You mean the first one? The first one, I think I put the 28th.
okay, so same day as the second test.
Yeah. So basically, you come into the second test, you we'll end class there. Oh, boy.